Yes. Thank you very much. Can I use this one as well, or? Yeah, right. Can I walk around a bit? Right. Hello, everyone. I'm Martin, as introduced. Thank you. And today I'll be talking how we intend to go from RAG to riches using our enterprise search application. So I'll talk about this application that, of course, I didn't develop myself. There was a whole team behind it. I'll show you in the end, just so you know. Right. So there's been quite a lot of hype around RAG, right? Big tech companies have been building products as well, which are usable by us, right? Bing Chat was developed basically by coupling ChatGPT to Bing in February 2003 already. And then Google came along with, in my honest opinion, a slightly better search engine and a slightly worse model to make Bard. And then we have ChatGPT search that was launched quite recently. So now that these big companies have these models out there, is this a completely solved problem? Well, we think not. I think there's a lot of use cases, especially for closed data and specific use cases where there's a lot of use for building more specific applications. So let's start at the basics a little bit. What is RAG? So basically it's often set off against just question answering a large language model. So here are two flows. One is question LLM answer. The other one is question information retrieval LLM answer. So you can do either one, but doing regular LLM QA has a few problems. This has been discussed at length today, so I won't dwell here for too long. But you have fixed knowledge during training. You're prone to hallucinating. So any programmer here will probably know that if you ask it to give you some arguments to your command line utility, you'll probably get some very likely sounding things that don't work. And it doesn't have access to specific data and would be very costly to train into your proprietary data that you have, for example, technical documentation in the company. And RAG seeks to address this by giving it access to, for example, your company database with technical documentation for the product that you've developed, and have more up-to-date information, for example, as it actually reflects the state of a data set or search engine result. However, often in these kind of systems, you have to be up to par with your information retrieval part, because if that fails, then the application will behave a little bit poorly. So at Sopra Steria, we're a consulting company, so we build a lot of these RAG applications at clients. So what we do is both proof of concept work and bringing these concepts to production. And what we often find is that clients of ours have a lot of data privacy concerns, so they really prefer not to send all their data to the public cloud. They also often encounter a lack of integration with these proof of concepts. So an information retrieval system really only gets useful when you have access to a lot of information, because otherwise, basically the whole point of it fades quite quickly. We find that often these proof of concepts can have an over-reliance on generation, and a design that is really, I call it naive here, but it's really focused on quickly showing a point. Now, what we started doing recently in a few of our clients is integrate these systems into the IT landscape, so really connecting it to the actual up-to-date databases that clients have. I call it air-gapped here, but running it on systems that don't have internet access, so that's a especially tricky thing where you have to make sure that you only use open source modules that you hook up together yourself. And we did a lot of work on making these things run more stable, because the peak loads on these models can be quite high. Right, so doing all these projects, we found that there was room for a product that we could make ourselves. Because a lot of different customers had quite similar needs that we could solve if we built a product that would run anywhere. So either having internet access or in the cloud, or running on a private data center, or even on a laptop or a mobile phone. So this gives us some boundary conditions that we'll come to later. Has to be modular and extendable, because clients often come to us for very specific use cases. For example, finding certain products in a database of laws. So for this, you can really take some time, tune your system to behave better for this specific use case. Therefore, it has to be configurable, and it has to be scalable if eventually we would like to get this into production. So functionally, what we build is the system here. So starting from left, where the data comes in, we have different data collectors where, for example, we can scrape websites. And we do this for permission because often the people that hire us find it most easy to just give us access to their website instead of finding the data somewhere in a database. We can take as input, for example, XML documents, which are often used in laws, but also more typical PDFs and that kind of data. Then we have a data ingest pipeline where we, as needed for LLMs and embedding models, cut these pieces of text. One trend that's been gaining some favor lately is adding text to your chunk to talk about the general context of the document so that the LLM actually knows what the piece of text came from. But you can also do things like adding metadata, which year was it published, that kind of stuff. Right, then you put this into a vector database. So we're actually using Weaviate, so if anybody wants to see that talk, that's actually the product we use, so we'll get to that later. Then in this vector database, you can do similarity search of different pieces of documents that you found, of course. To get these embeddings, we have a service for running embedding models, either locally or through a public API. And the same goes for language models, so we can use any model that you can pull from Hugging Face, but also ChatGPT or Claude. Then there's a backend server that handles all the queries and gives you the retrieval results. And if you want so, you can get generation as well. And then we have a few demonstrator front ends because basically the product ends here. But if you want, we can add a front end to that. Now, in terms of architecture, there's a few things that are very important when you design a system like this, especially if you want to use it in production. So first, you have to make sure, for our use case at least, that you can turn modules on and off, because every use case might need a different combination of models, but also generation, yes or no. For example, the police, we are working on an application there where we retrieve instructions for officers on the street on what to do. And there they found that the risk of hallucination was especially high. So, for example, we turned the generation module off. Or we decided not to make a generation there. So you would like loose coupling so that when a new thing pops up, you can integrate that readily. So one thing we find is that models that are the best in class now might be outdated in a few months. So you need to be able to change those things quickly and also be able to add new things that come along. For example, agentic workflows were not a thing 2 years ago, but now they're really taking hold, so we need to be able to integrate those. And then for scalability, in a room full of software engineers, I'd be hesitant to call this a microservice architecture, but for marketing purposes, I think I could. But the main point is we can scale some of these things independently. So we can, when the language model is busy, we can spin up some extra language models. If the embedding service is busy, you can increase that. Or if you want to ingest a lot of data, we can make sure that there's enough capacity to do that. So basically scaling the CPU-bound tasks mostly. And then, of course, so as told, we need support for the new things. Right, and now that you have a system like this, you use typical methods like CI pipelines to make sure that you don't destroy it when you make a small update. But for the machine learning part, it's a bit more tricky, right? Because you have to do some kind of metrics to make sure that you're actually improving your model when you intend to. And of course, there's method like MLOps that basically give you a recipe for how to do this. But I think this will resonate more with you since we're in Groningen. Has anybody any idea who this guy is? No, probably not. He is Heike Kamerling-Honest. It's a guy from Groningen, Nobel laureate in physics. And I think his motto is really something that describes very well how you should approach this improving of these products. So he says, door meten tot weten. And he doesn't say meten is weten. So to translate to English, he says through measurement to knowledge. And not knowledge or measurement is knowledge. But as we'll find out in a few case studies that I'll describe, You can do some measurement, but automating this too much is quite difficult because there's a lot of hidden information in the choices that you make in modeling. Right. So what way we try to make this system better every iteration is by having different golden data sets. So these are evaluation data sets. Put it in our product, and then test for different configurations and see which parameters, for example, perform best. So now we mostly use the benchmark information retrieval, which is a published golden data set that has a few different languages and a few different tasks that it can do. And in the future, we would like to use synthetic evaluation data sets generated from client data, but this is something that's still work in progress. Right, so there's 2 case studies that I would like to discuss with you. First of all, there's which model works best for Dutch, and then what combination of keyword and vector search works the best. And this is also something that was covered partly in the Weaviate talk earlier. So for evaluating Dutch models, what we do is we have Robert, which is a Dutch model, and we have a family of E5 models, which were released by Microsoft Research, and they're multilingual. So we would like to see whether it's better for our clients that have Dutch data to actually use a Dutch model or a multilingual one. So again, we use this benchmark information retrieval, which is part of the MTAB embedding data set, or benchmark actually. But this, however, this dataset was multilingual. It was multilingual in the way that it was English and Polish. So we needed to do something there. And for this, we used Marine NMT, which is also the engine behind Microsoft Translator, to translate this dataset to Dutch. This is really a beautiful product. It's an encoder-decoder setup where you can, the encoder and decoder are in a specific language, and you can basically plug them to translate from and to your desired language. Right. So now there's a few different measures in information retrieval that are important. I will go through them very quickly. So there's recall, which is basically part of the confusion matrix. And if you have one answer for one question in your bag of answers, basically, then recall is the recall of 1 is the chance that you find the answer in your top one answer list. And the recall 5 would be the chance of finding your answer in the top 5. And then there's discounted cumulative gain, which is based on a few premises. It's a bit more mathematical, so I'll go just to the premises, which states that documents of equal relevance score higher when they are at the top of your result list compared to the bottom, and relevant documents should score higher than irrelevant documents. Right, so these are some results. So let's walk you through the axis first. So we have a few different results for the E5 model, and then for the Dutch model, and the Dutch model plus a re-ranker that we applied afterwards. And here we have the different metrics and the different data sets. So this is the English SciFact data set, and this is the Dutch SciFact data set, which are part of the benchmark information retrieval. And these are some cross-querying. So querying in Dutch to the English data set and querying in English to the Dutch data set. Now, what we see here is that a sanity check would be to see that the recall 5 is always higher than the recall 1, right? So the chance to find in the top 5 should be higher than the chance to find something in your top 1. And we see that this is indeed the case everywhere. What we also find is that these family models score better in any case really than the Dutch model. So for this specific data set, it's better to just use a multilingual model compared to a Dutch model that we found here. However, we found colleagues that used a different data set and they found opposite results. So it's here again, you can use a benchmark, but if this benchmark is not exactly the thing that you're trying to implement at a client, then you might be off. So you still have to do some thinking. But what we find is that also by applying a re-ranker, you can actually increase the results quite nicely here. So for example, here you see when we apply the re-ranker versus the regular model, we see that we can go up by almost 10% in these different benchmarks. So basically conclusion from here is use the E5 model for now. So then there's keyword versus vector search, which is also quite interesting because vector search is of course all the rage now, but keyword search is another way to quickly find a ranking of relevant documents. So again, we use these two different models and a few other ones, but now we also use Best Match 25, which is basically state-of-the-art keyword search algorithm. Again, on this benchmark set in our system. And here we see something interesting in the results. So on the x-axis here we see recall 5, so one of the metrics that I've explained before, so the odds of finding something in the top 5. Here we see the alpha parameter, which basically states how much vector search we're using. So 0 would be only keyword search, and 1 would be only vector search. And we can see here, of course, that when you don't use the vectors, all of the different models score the same. So again, sanity check. But what you also find is that if you use, for example, a BERT Dutch model, that actually just using keyword search is a lot better than just using vector search. So you need a certain quality of models to actually have use for this vector search. But what's also interesting is that even though this BERT model doesn't do very well on its own, it can still make results better if you add a little bit of it to a regular keyword search. So basically, this tells us that, well, in many cases, you never really want to truly only do keyword search. Then these are a few different models that we use. The Robert model was on the previous slide, but for now I'll stick with this one, the E5 model, which was also on the previous slide. So what we see is that this E5 model performs a lot better in just vector search, actually better than performing only keyword search. But also this one gets better if you use a combination of the two. And this is a trend that you see in all of these models. So depending on how good your model is, if you have a relatively bad model, you should use a bit more keyword search. If you have a very good model, you should use a bit more vector search. But for now, we'll keep this parameter at 0.5 since we're using this E family of models. Right, so using this kind of benchmarks, I think, is a very good way to make sure that you're actually improving your system. But one of the dangers, of course, with these golden data sets is that the data set do not actually describe the use case that you want to implement. So this is something that we want to tackle in the future, where we can benchmark on customer-specific data sets. Also, we'd like to integrate this into a pipeline that automatically evaluates the system. Maybe not every commit, but on every day or something like that. And also something that we still have to add is the LLM-assisted evaluation to this. And I promised that we went from rag to riches, but unfortunately we haven't achieved the riches quite yet, so also that's something to well, look out for in the future. Then I'd like to thank the whole team, because I didn't do this alone, of course. It was a group effort. And unfortunately, my colleagues Max and Bob are still missing from here, but also they contributed nicely to this project already. With that, I would like to thank you for your attention.